my goal today is to calculate pi with Atari BASIC. So the plan is, let me think here, GR period 7. Boom. So the plan is we're gonna find the square root of 2, and then we're gonna multiply that by 4, or actually 2, because it's square root of 2 over 2 is 45 degrees, or pi over 4. So if you multiply pi over 4 by 4, you get pi. And so first things first, maybe we should be writing a program. Graphics mode 7, 10, 10, and then color 1. So 10, 20, plot, horizontal 50, comma 50, and then 10, 30. We're gonna draw a point starting at 50, 50, 50, and going out to 100, vertical 50. And then 10, 40, we're gonna go back to comma 50. Let's run, see what happens. So we got that at 50, 50 is our point of origin. And then straight out from there, let's draw another line. We plotted at 50, 50 the last thing. So then at 10, 50, we're going to draw straight up. Okay, so dr horizontal 50 and vertical 0. See if that works. So there's a 90-degree angle. And now if we calculate the 45-degree angle on the unit circle, it'd be a 45-degree angle, and you want 50 degrees distant on both x and y coordinate plane. Go to the graphics mode 0 so we can see this better. To this page here, it's got the Atari BASIC reference manual, the 8-bit Atari BASIC manual, and what we're looking for is square root. So here's functions library, and the square root is on page 34. There's square root. So you just put square root and then SQR, and then you put parentheses around it. So we're going to calculate the square root with a numerator and a denominator in two separate variables. Error at 3, line 180. 180. Didn't like that. We did 100 that way and 100 vertically, or 50 vertically. Let's print X instead. See what we're doing. See if we're getting a ridiculous number. Yeah, see, we got 70, which is too big. We should be getting a number that's less than 50. Let's get rid of the hint just to see what we get otherwise. $70. That looks like a square root of 2, but it's 100 times too big. So maybe we should do the square root of 2 to begin with. So if we just find square root of 2, and again, this is just for visualization purposes, we're going to find a very accurate rendition of pi. So let's figure it out here. Yeah. So square root of 2, but we need to divide it by 2 to get the sine and cosine. Maybe that's why we're getting 70. It's because we weren't dividing by 2. So let's divide by 2. And then, let's run it again, just to be sure. Yeah. Square root of 2 over 2. And then, so this, if we multiply it by 50, we should get the right answer. Times 50 plus 50. So try it again. Plot 50, comma 50, 1080. Plot. I actually draw 2. GR period. X, we're going to go 50 plus x times 50. And then here we're going to go 50 minus x times 50. There we go. Now let's see what that does. Yeah, there we go. So that looks like a circle around there. So that's our 45-degree angle. And we're going to calculate the vertical and horizontal lines using calculus. And then we're going to multiply it all together to get the square root of 2 with a numerator and a denominator as close as possible as you can get with the Atari without any tricks. We're not doing multiple sets of 2 variables. We're just doing a horizontal and a vertical, and we're going to calculate the square root of 2, and then we're going to multiply that by 4. Actually, multiply it by 2 to get pi, and we'll see how close we get. So and see how few iterations we can get it to work at with just a numerator variable and a denominator variable in Atari BASIC. So we need to look at some limitations. We need to find out what the biggest number you can get in Atari BASIC. We'll find that without going into exponents. We just want an integer. We want an integer without exponents. So we can start by doubling. Let's see how many bits we're using. So let's at 10 90, we're gonna for x equals 0 to, let's try 500 colon next x for our delay, and then here we're gonna go back to graphics 0, graphics text mode, and then 1110 we're gonna figure out, we're not gonna find it fast, we're gonna find it accurate. So we want to test how big an integer we can get without going into exponents. So we'll start with x equals 1, and we'll go 1120 x equals x times 2, and then we'll find out how many bits we're using. And, well, just as big as we can get without exponents. So 1130, at 1130, if and we need another one, y equals x. Actually, we want to put that on a separate line. And we go 1115 y equals x, and then 1130 if x is less than, y times 2, then we know we've hit the top. So then go to 1200. Otherwise, we're going to go back to our y equals x. 4115. We need to print. Control 5. So we need to print the results at 1200. Why? I don't know. This might not work because it keeps shifting the bit double, and then it would hit the exponent and it would still do it. We should start with, so maybe we should just continuously print the results until we hit an exponent, and then see what we're doing. Let's get rid of 1115. Let's get rid of 11. Well, let's list 1130. We're going to get rid of. We're going to get 1140 out of the way. And we'll move print to 1130. And we'll do our go to at 1140. Go to 1120. We need to print x. 1200 go away. We need to print x and not x. All right. We need some time to look at it. So we need a for loop that'll just wait. So after the print, it'll wait a bit. 1135 for y equals 0 to 500. Next y. That's too slow. It'll get there, but it's too slow. Control break. That's too slow. Let's do a fifth of that. Whoever knew Atari was doing these big numbers. Oh, there we go. Break. Oh, crap. So let's run that again. A little slower, just so we can. How do we do a break? Actually, we need a counter that counts how many bits, too. So, and a little faster than that. Let's do 150 here. And so we need the iteration. So we'll go colon n equals 1. So that's the power. And then we'll add 1 to it each time. And then we'll print n comma x. There we go. So it looks like 33 bits. We're using 33 bits. Break. So 32-bit number over a 32-bit number to get a 64-bit number. Numerator over denominator. So we get about 64 bits of accuracy. Maybe as much as 66 bits of accuracy. All right, so let's change this just to see. So we started at basically 2, the first power of 2. 33 bits. Let's make this even more accurate. So we know about 33 bits, but we don't know exactly the biggest number before it hits exponential expressions. We want it to go like go. And then let's see, 11, 15, back to that, 4, n equals 1, 2, 33. And then down at 1140, we're going to go next n. Actually, we're one ahead of it on actually, oh, I doubled n for some reason each time. I added 2 to it each time. So we need to take 1120 and fix it. That's better. So we did 33 before. And we got there. Let's try 34 just to see. Just to see if we're 34. Just to see if we hit an exponent. Yep. So 33 doublings. We got 33 bits to work with. We don't know exactly how big it gets before. So let's try a little bit bigger than 34. Let's make this 33. And then down here at 1140, we'll do 50 and go x equals x plus what? Let's see, a good big number to start. A good big number, halfway. See if it'll go a little bit further. So halfway of 33 bits is 32 bits. Let's go smaller. 30. Let's try 30 bits. So 2 raised to the 30th. 2 raised to the 30th. Let's get the regular Atari calculator out here. 2 raised to the 30th power equals that. So if we do x plus this number, so it's 1, 0, 7, 3, 7, 4, 1, 8, 2, 4. Then we'll just loop over that until we hit an exponent. We could shrink it up a bit. Yeah, it's gonna do like 4 doublings and then, or four iterations of that will be over. So maybe a smaller number. Smaller number. Let's divide by 2 or something, or divide by, I think, 16 iterations would be pretty good. Maybe 30, 40, 30, 60 iterations of that. So let's plug this in. Thirteen, 4, 21, 7, 7, 2, 8. All right. Let's list it again. So we need to do that over and over until we hit an exponent. We need to print out the results. So print n comma x. And then what? We need to start in it n equals 1, and then at 11:55 we're going to go n equals n plus 1. So all this is just to figure out what the biggest number I can represent in Atari BASIC without an exponent. So I don't think any of the documents will tell you that. Nope. I need a loop. I need a loop on that. So we need to start at 0 here, and then we need to loop. All this to figure out what the biggest number I can represent without an exponent. Atari BASIC's cool because it does these rather large numbers without any extra coding. Whoops. Too fast. Too fast. I need a delay statement. So 1174 y equals 0 to 150 next y. So where does it hink up? Where do we end up getting an exponent? Oh, come on. Forgot the go to. 1180. Go to what? 1150. I want a really accurate pi, so I'm trying all sorts of tricks in the book. And the exponent would just ruin the accuracy because it wouldn't be. Ooh, look at it go. Probably 999. Yeah, it's all nines. It's a binary coded decimal that we're working with here. Let's just confirm that. Let's just confirm that. Hmm. Hmm. Let's just confirm that. So that's 33 bits would be 30, which would be 3 times 3 digits. So it's 9 digits, maybe 10 digits of 99999. 10 digits of 9. Let's try going 1080. 1080 x. Let's do. Looks like it's all nines. So if we did find out how many you can do without busting it. 11 1147 for n equals 1 to 1155 we got to get rid of. Then over here we're going to go see it does all nines. Gets up to 99 and then it starts doing exponents. So we got up to 10 iterations before it broke out. And how many digits do we have? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits of nines. It's the biggest number we can get to. Let's just confirm that. So looks like we got up to 10 with the n, so we know what to do. Let's change this to 10. I could shrink the time delay down so we don't have to wait all through this. And just eliminate the time delay and you just see the last thing that came up on the screen. So let's do that. Let's get rid of let's just shrink it down to something small. 100. Get our delay statements so that they a little shorter. Might shrink them some more later down the road. Just make sure we got them in. It's faster. We still have a pretty big delay statement, 100 loops of next. Let's make them even shorter. Let's do, that one's okay. This one, let's just make it 10. Same with this one, just make it 10. That's better. So 10 digits. 10 digits of nines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's binary coded decimal that we're using here. That's something that the 6502 had, but it got phased out later when we started going bigger numbers with binary, more efficient storage of numbers with binary and binary coded decimal. And so right after this, I'm going to test if all nines is the biggest number we can show. So 10, 10, so at 1190, we're going to go x equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1200 print x. What? Nope, it didn't like it. I didn't get another 9 in there. I got a 0. The 10th one was 0. Let's see if we can do 10th 9 is 0. Actually, I may have typed it wrong. Let's try here. No, it didn't like it. And it changes it in the code. Let's see if we can do 5. It didn't like 9. Nope, it doesn't like that last digit. It doesn't like that last digit. It changes it in the code. Yeah. So it looks like 9 nines might be the only hope. Let's change this number to an 8. And this back to 9. See what that does. Nope. It doesn't like 10 digits. It likes 9 digits. So looks like we got that as our biggest number. Without exponents. Yeah, see, it does that fine. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. That's the biggest number we can represent without an exponent. So, next step. So, we're going to do calculus in Atari BASIC to calculate pi. And we're not going to use the square root function because it's gonna screw with our integer formulation of pi. We want a numerator over a denominator that's 9 digits over 9 digits. Hmm. 9 digits over 9 digits of pi. Maybe 9 digits over 8 digits. I don't know. So we want to find out the square root. And the square root of 2. Square root of 2 divided by 2 is pi over 4. So you can do square root of 2 times 2 and you get pi. Square root of 2 times 2 gets pi. So finding the square root without the square root function, because it's going to mess with our number theory. 9 digits over 9 digits. We'll get a more accurate square root than the Atari BASIC will give us, but let's see. We'll use multiply. Have to use multiply or write your own, but Atari does multiply just fine. So we're trying to find the square root of 2, and then we'll find the difference. Numerator over denominator, just parallel multiply. That would be the square. And so at 1230, should probably have a print statement in our, actually it didn't work. Actually, we're finding the wrong number. It's squared, so we need 2. X is greater than 2 instead of 4. X 2 2 2. All right, and we should put the print statement at we should put that print statement inserted in here. 1255. Put another print statement, and then at 1300, we're gonna go print quote PONE. Print done, and then here we'll print results. Yeah. It doesn't like it. It didn't like it. It just did it right off the bat. That's not the square root. Oh, it shouldn't be 4 there. It should be 2. It should be 2 here. Oh, it's not going anywhere. How come it's not going anywhere? So x always equals 2. Is that it? Let's make this different. Let's do 3. Make D 2. Maybe that'll fix it. Yeah, there we go. Now we're thinking. Oh, we're getting out of control. Escape. Control. F function. F5. So it's out of control. So so we need to look at the let's keep it under control by doing this. We go if n is greater than 999999999. Actually, it should be smaller than that because that's the biggest number. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then do the same for D. $53 D. There's our answer, I think, for square root of 2. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And looks like that's what it came up with. So what do we get? That should be the square root of 2 right there. Let's say no. That's the wrong answer. It should be 2 exactly. Numerator over denominator. If it's greater than 2, increase the... Oh, we need to change the 4 to a 2 over here. We could probably dispense with all the other stuff. Doesn't seem to be getting any closer. Actually, where if we've landed on the same number every time. So we need to be increasing the value rather than getting a floating point value. So we shouldn't be dividing by 2 maybe. And we should be turning this into an integer. the goal was to have that represented as a whole number ratio, a positive numerator and a positive denominator as whole numbers in a proper fraction. But I'm getting the right numbers now, and this is what my program looks like. See, I'm calculating the epsilon, which is y, the absolute value between x and 2. And that's the epsilon. And you add the epsilon to the numerator if your square is less than 2. And you add the epsilon to the numerator if x is greater than 2. And that way you get closer and closer to the square root of 2. And apparently the Atari mathematics gets an epsilon as low as 1 to the minus 10th. 1 times 10 to the minus 10th, at least. And if I crank this up to 15, maybe it'll break it. I don't know. Let's try. Well, still cranking. Let's see how close we got. 3.268744213 divided by, let's look at that. Looks right. And then divided by 2.311344972. That looks pretty close to square root of 2. Let's print SQR2. Right on the money. Right on the money. So the only thing left is to somehow rationalize it into whole numbers, because I like whole numbers. An integer processor can calculate integer numbers. It gets confused when you start, moving the decimal point around. So I'm working on a way to get it into whole numbers, so I can have my virtue data processor process it to an exact value with a 64-bit numerator and a 64-bit denominator, and as whole numbers, not fractions, not floating point, not exponential. So how do we get it into integers? So the epsilon gets smaller and smaller, but the numerator and denominator stay relatively the same. So we have to somehow put it on the scale of the epsilon and crank it up into an integer. So I've decided to add a scale variable. That's this S up here. I'm going to add a scale value. I'm going to double it every time I can figure out if D or N or has anything on the right side of the decimal point. So there's that. And I want to stick it in its own little segment, and we need to do that here. So at let's start small. 1252. And we go if d is greater than int d, then if d is greater than int d, then we double everything. We d equals d times 2, and n equals n times 2, and scale equals scale times 2. Then we do the same thing for n. In the next two numbers away, let's just come up here, 4, and then we go n and n, and then we double everything, and so we need to scale our y factor by the same scale, and we gotta come over here and go times scale, and let's list that. And see how we do. Actually, we're going to have to test those numerator and denominator, see if they've exceeded our integer limit. So that's going to replace this guy, and if n is greater than 9, 1, 2, 3, 4, 5, 6, 7, 8, then go to 1300, and on the next line down, see if the denominator has done that. So let's list. Now we got these funny little, because it's only 40 columns. We can't manage more than 40 columns on the Atari screen. Just wait till I get Atari working in a JavaScript browser, and have 8 by 8 pixel characters on a 1080p screen. I got that going elsewhere, but tonight I'm all about the calculus in integers. So we need to crank that over and over until it passes. So, maybe we should put it in a subroutine, and I don't know. Maybe we need a go-to at the end of that. So come up here and put in a colon and go to its own line. 12, 5, 2. This is confusing. 12, 5, 2. And then this one, go to 12, 5, 4. Until it doesn't work. Until it doesn't have anything on the other side of the decimal point. And we're only multiplying by 2, so it's not a full decimal point. It just keeps going up until it's an integer. All right, run. See what happens. Yep, here we go. Well, it's hit a stable value, not changing anything. So how do we tell? So maybe if we find that y is 0, if y equals 0 at the scale, it's exactly 2. So we'll change these. If y equals 0 and that, we'll just remove 1270. Because apparently that's what it was doing before, was hitting 0 and then nothing changed. Yep, found it. Looks like we have integers. Woohoo! Does it work? 2, 1, 9, 6, 1, 5, 48 divided by 1, 5, 5, 1, 1, 2, 0, 3, 8. 1 point. Oh, it's lost a decimal point. It's lost a decimal point. How did it do that? Maybe maybe it started out wrong. I don't know. So how do we fix that? We put what? We put a. Let me take off the. Well, we can go period 8 like this. Yeah, but that's the wrong value. That's not right. 1.14159. Is that? I don't know. Let me see. SQR of 2. I don't think that's right. No, it's not. So somewhere along the line we messed up. So we're scaling them all the right way. We just didn't scale in the right mode. I think we multiplied y out of scale. So we need to do the scaling before we need to do the scaling before we do the calculation. Maybe at 1220, right after 1220, twelve 22, and 1224, and And if the y shrinks down to 0, then we're done. And now we have to fix the 2 lines we moved. So 12, 52, 12, 54. Error. What's error 12? Error 12. It's probably like out of range or something weird. 12. What was our error code? 12. Error code 12. I'm going to look that up in my hard copy. Yes, programming is not for the faint of heart. You have to research everything. So, error code. It's not in Appendix I. Appendix G? No. Appendix D. It's a character set. Appendix D. And then, yeah, they put the error codes on the wrong page here. Don't know where to find it. Error codes. There we go. Error messages. Error message 12. Line not found. So I moved that, and now it doesn't know where one of my go-tos are. Is that what we had? Let's reduce this. Yep, error code 12. Line not found. Let's see where it went. It's line 2, 2, 2, 2. Okay, I think I know. I think I know what I did. I moved the lines, but I didn't move the numbers. Yeah, I still say the wrong place. 2, 2, 2, 1, 2, 2, 2, and then 1, 2, 2, 4. Let's try running it now. Well, it seemed to work, and got some nice values, so 2, 1, 9, 3, 6, 1, 5, 5, 5, divided by 1, 5, 5, 1, 1, 2, 0, 4, 3. That looks better. That looks much better. So, PRINT, SQR2. Right on the money. So I got my integer results finally. Congratulations, to pat myself on the back. So I'm going to save this. Save, quote, D colon, SQR 2. Wonder if it'll accept that as a file name. Don't know if it'll do that. Well, let's go to DOS. Make sure it's there. Square root. It didn't like the parentheses. Oh. So I need to fix that. Let's go to basic and load. It's just B1:SQR. No extension. Looks like it's there. Let's run it, make sure. Yep. Looks like it works. So L period. So that's how you do calculus with integers alone. Isn't that nice? So you just multiply them by 2 until you get rid of that decimal point. Multiply everything by 2. You multiply the scale, the denominator, and the numerator, and it all works out fine. But you got to do that before you do your epsilon. You got to do that before you do your epsilon. So let me save it as a different file without parentheses this time. SQR2.BAS. DOS. Yep, square root 2 base. There we go. So let's look. Let's clean it up a bit. You don't need any of that garbage before 1200. Except for maybe GR period 0. So we can go new. And then come up to the right spot. And then let's list. Dinky little program. So at let's try 1100. I'm going to go GR period 0. And let's run it, make sure it works. Looks like it works. Yep. Integer square root of 2 as a fraction. So print 219361555 divided by 15512112043. Yep. And then we should try it in the Atari calculator or the Mac calculator just to make sure. See how close it is. So 2, 1, 9, 3, 6, 1, 5, 5, 5 divided by 5, 5, 1, 1, 2, 0, 4, 3. Change the sign, see how it differs. Well, pretty close. Pretty close. How many digits did we get? We got 1, 2, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits of accuracy, and we only had two 9-digit numbers. So I'm going to do that with 64-bit numerator and 64-bit denominator, all as integers, and we'll see. See if we can make it happen.